Welcome to this explainer. We're diving straight into the broken math mystery, zero point 0.1 plus zero point 0.2. If you've ever written a simple math equation in Python and stared at the screen thinking your computer is playing a practical joke on you, well, you're in exactly the right place. Let's pull back the curtain on this infamous programming gotcha. So, does zero point 0.1 plus zero point 0.2 equal zero point 0.3? I mean, mathematically, absolutely yes. But let's see what Python actually thinks about that assumption. You run the code, and instead of a clean 0.3, Python spits out 0.3, followed by a ridiculously long string of zeros and a random 4 right at the end. And if you try to verify that using a double equal sign to compare it to 0.3, Python literally tells you it's false. Okay, it's not a bug, and you are not doing it wrong. Seriously, if you've ever spent an hour debugging this, thinking you somehow broke basic arithmetic, take a deep breath, your machine is totally fine, and Python hasn't forgotten how to do math. What we're actually looking at here is a fundamental truth about how computers process information. To really get this, we need to look under the hood. Python, just like pretty much all modern programming languages, uses the IEEE 754 standard. It's a 64-bit double precision float standard. Basically, it translates our human decimal numbers into binary using exactly 64 bits of memory. And since memory is finite, our exact precision gets capped at about 15 to 17 significant decimal digits.
Here's the absolute best way to think about it. In base 10 math, if I ask you to write down exactly 1/3, you can't, right? It's 0.333 repeating infinitely. You'd literally run out of paper. Well, computers do math in base 2 binary. And in binary, a simple fraction like 1/10 or 0.1 creates that exact same infinite repeating sequence, 0.000110011, and on and on. Because floats use this binary representation, simple decimals like 0.1 and 0.2 just cannot be stored perfectly. The computer is forced to chop off that infinite sequence at a certain point. So when you add those chopped off numbers back together, you get these tiny rounding errors. That weird 4 at the end, it's not a glitch. It's just leftover math residue from translating base 10 to base 2 and back again. Now that we know why this happens, let's build up your arsenal. We've got 3 main fixes: round for display, math.isclose for comparison, and decimal.Decimal for exact math. All right, fix number 1. If you just need to show a nice, clean number to a user on a screen, the built-in round function is totally your best friend. Just wrap your math in round, tell it you want 1 decimal place, and it elegantly trims off that messy binary residue. You get a perfect 0.3. Super quick, totally painless. But what if you're writing an if statement to check a calculation? We already know a double equals comparison will fail. So fix number 2, import the built-in math module and use math.isclose. This brilliant little function checks if 2 values are close enough to be considered mathematically equivalent, and it safely returns true. And this brings us to a massive takeaway. You've got to train yourself to completely abandon the double equal sign when comparing floats. Honestly, using double equals here is like laying a landmine in your code base just waiting to blow up. Always reach for math.isclose instead. But hey, sometimes close enough just isn't good enough, right? For absolute precision, like when you're dealing with financial calculations, taxes, real money, we bring out the heavy artillery, the decimal module. This forces Python to do exact decimal arithmetic, completely bypassing those binary limitations. 0.1 plus 0.2 finally gives us a perfect 0.3. But wait, before you rush off to rewrite your entire codebase with a decimal module, I have to warn you about a massive trapdoor. It's easily the #1 mistake developers make with this module. Burn this golden rule into your brain. Always pass strings to decimal, not floats. Seriously, if you pass a raw float in there, you have lost the battle before it even starts. Here's exactly why. If you call decimal and feed it the raw float, 0.1, Python evaluates that float first, which means it instantly inherits the exact same binary inaccuracy we were trying to escape in the first place. It drags all that garbage float error right into your supposedly pristine decimal object. Just wrap your numbers in quotes so decimal parses them purely as text first. Let's lock this all in. Avoid comparing floats with double equals, do not pass bare floats to decimal, and definitely don't use regular floats for money. Instead, build bulletproof habits. Use math.isclose, always pass strings to decimal, and mandate decimal for anything financial. Now, as a quick bonus tool to round out your math kit, what about exact fractions?
What if you're not doing money, but maybe recipes or perfect ratios, where you need exact thirds without losing a single drop of data? Python actually has a built-in fractions module just for this. By using it, you define numbers exactly as numerators and denominators. Add 1/3 and 2/3, and you get a perfectly exact whole number, 1. It completely bypasses all that floating point mess, keeping the math beautifully pure.
So you now have the tools to conquer floating point math without breaking a sweat. You know the binary reality and you know exactly when to use which tool. But it definitely leaves us with a lingering question. If basic arithmetic is this much of an illusion in code, what other fundamental data types are hiding secrets right beneath the surface? Keep exploring, keep questioning, and we'll see you in the next explainer.